Hi everybody, I hope you're having a nice weekend. Our first video is going to be on the generic properties or general properties of acids and bases, which we covered a lot in chapter 4. So this should be all review for you, nothing absolutely new. One thing you have to know is how acids taste. In fact, I just had a clementine, which is loaded with citric acid and ascorbic acid, and it was pretty sour. It wasn't very sweet. So acids have a sour taste. Think of lemons, okay? Bases are also known as alkalis. And bases always have a slippery feel. When you think of the taste of bases, think of soap. If you've ever gotten soap in your mouth, whether accidentally or on purpose, you know that bases taste bitter. Bases taste bitter. And finally, I think this is having a hard time with this page, the feel of bases, think of soap, is slippery. Okay, you always know if you get a base on you because your hands get super slippery. One of the things students don't recognize is you know that concentrated acids are very bad for you. They're caustic. Bases are also very bad. Concentrated base does as much damage, if not more, than a concentrated acid. So bases are just as bad for you as acids are. We have to talk about some definitions. One of the definitions we have to talk about is that of an Arrhenius acid. Oh boy. So an Arrhenius acid is something that produces hydrogen ions as the only positive ion in solution. A hydrogen ion is abbreviated with an H+. So it's very easy to recognize an Arrhenius acid because H has to come first, or the Q group. And again, probably very much review for you. Or we can have the Q group. So to recognize an Arrhenius acid, you either look for H first, or you look for the Q group. Okay? An Arrhenius base is something that produces hydroxide ions in solution. As the only negative ion solution, which are OH minus. So an Arrhenius base is pretty easy to recognize because it's a metal with OH. So for example, like NaOH or FeOH3. Those are Arrhenius bases. They're a metal with OH, okay? Another definition of bases, which is more general, is the Bronsted-Lowry definition. Okay? A Bronsted-Lowry is more general, and a Bronsted-Lowry acid, though, is pretty much the same thing. They're defined as proton donors. Remember, if you do acid, you're a loser. Meaning you lose protons, right? So if you do acid, you're a loser, you lose protons. So proton is simply just an H+. So really the Bronsted-Lowry acid is the same as the Arrhenius acid. The only difference is we use the word proton instead of the word H+. A Bronsted-Lowry base is much different than an Arrhenius base. It's more inclusive, and what a Bronsted-Lowry base is a proton acceptor. You gain protons. So of course, all the metals with OHs are still Bronsted-Lowry bases, but also some things that don't have OH. Okay? So you don't need OH to be a Bronsted-Lowry base. All you really need to do is to gain protons. So for example, like NH3 is a Bronsted-Lowry base, or CH3NH2 is a Bronsted-Lowry base. They can gain protons and become NH4 plus or CH3NH3 plus. Okay? So they're proton acceptors. So it's very easy, and again, this is review also from chapter 4, though some of you had problems with this on your final exam from the first semester. It says, determine the Bronsted-Lowry conjugate acid-base pairs in the reaction. So to find the acid-base pairs, okay, the first thing you want to do is partner them up. And the next thing you want to do is count the hydrogens. And the partner with more hydrogens is the acid. The partner with less hydrogens is the base. So here we go. When I say partner them up, you ask yourself, who is water going to turn into? Which product does it look most like? In the product that you pick, its partner will either have one more hydrogen or one less hydrogen, and that's it. So H2O partners with H3O. They are a conjugate acid-base pair. Now we have to figure out who's the acid and who's the base. So after we partner them up, we count the hydrogens. Shh. This has 2 H's. This has 3 H's. The more H's you have, you are an acid. So this is the acid, and this is the base. And since this is a reactant, we just call it base. Since this is a product, we call it the conjugate acid. Okay? In other words, how would H2O become H3O plus? To go from here to here, it would have to gain an H. And if you gain an H, you're a Bronsted-Lowry base. So its partner is the acid, because if you go in reverse, it would have to lose an H to become H2O. HCl is partners with Cl minus. And again, how would HCl turn into Cl minus? It would have to lose an H. If you do acid, you're a loser. Again, the one with more hydrogens in the partnership is the acid. And so its partner is the conjugate base. Because how could Cl minus turn into HCl? Oh, Cl minus would have to gain an H. Okay, and if you gain an H, you're a base. Lose is acid, gain is base. More protons acid, less protons base. Super easy way to determine. So notice the reaction's reversible. In the forward reaction, you have H2O reacting with HCl. And in the forward reaction, what's happening is the proton is, this is acting as an acid, this is acting as a base. So the water is pulling the hydrogen to it to become H3O plus and Cl minus. That's what's happening in the forward reaction. But there's also a reaction happening in reverse. In the reverse direction, right, you have H3O and Cl minus. And Cl minus is attracting the proton to it to give you HCl, hi, and H2O. We have a friend. Okay, hold on just a second. Oh, I think we're recording. So anyway, there's competition in the reverse reaction, or there's competition in the reactions for protons between our two bases. Water is attracting the proton from hydrochloric acid, and chloride is attracting the proton from H3O plus. Okay? So both reactions are happening. All right? There's double things going on here. The stronger the base will determine whether water is a stronger base or Cl minus is a stronger base will determine where the equilibrium lies, and we'll get into that later on in this chapter. Okay? Okay, things we have to be able to do is write equilibrium expressions for weak acids dissociating. Okay? Strong acids will not have an equilibrium constant or equilibrium expression. But if you have a weak acid, which I'm just going to designate HA, weak acids react with water. Water acts as the base and pulls the proton off of the acid. And that gives you H3O plus and A minus. So we can write an equilibrium expression for this reaction. K would equal the concentration of H3O plus times the concentration of A minus over the concentration of HA. Pure water is not written in solution or in the equilibrium expression because it's a pure liquid. We do not include pure liquids in the equilibrium expression. Oh, by the way, since with this K is for the acid dissociating, we call it Ka. All right, because it's a K for acid dissociation. More often, though, when we write weak acid dissociating, I do not include the water since it's not included in part of the equilibrium expression. So it's easier and honestly more acceptable to just write HA goes to make H plus and A minus. And so what you would get if you were writing the Ka for this expression is Ka equals concentration H plus times concentration A minus over concentration HA. H plus and H3O plus are the same thing. This is the hydrogen ion, and this is the hydronium ion. But they are equivalent to each other, okay? We can use them interchangeably because the reality is if an acid dissociates in water, the proton does not float around all by itself. The proton will be attracted to electrons on oxygen's head. And so there'll be a bond that forms here to generate H3O plus. So if you could really look at it with your Miss Frizzle glasses, you wouldn't find any H plus by itself. It would exist as H3O plus instead, which is why we can use those interchangeably. Okay, so we can only use Ka for an acid dissociation. For this general reaction that we had up there. Not when you're reacting an acid with a base or anything like that. Okay, so, oops. Let's try to write a couple. Letter A, it says write the dissociation reactions for each of the following. So we start with our acid. Again, I do not include water because it just is more complicated. Make it easy. This dissociates into H plus and Cl minus. Okay? Acetic acid, HC2, H3O2 will dissociate into H plus and C2H3O2 minus. I'm going to do letter D, or E, excuse me, and then I want you to do C and D for me on your paper. So letter E, we're taking the hydrated aluminum ion. Okay, this is what we're taking. And it's going to lose a hydrogen. Well, really, the only place it could lose a hydrogen from is water, right? It is aluminum with literally 6 water molecules around it, right? 6 waters like this. I think it's easier if I draw it for you to see, though you don't have to draw it on your paper. So the aluminum ion is hydrated. What do I have? 4. I need 2 more. 5, 6. Oops. And what happens when this acts as an acid is one of these waters breaks apart into H plus and OH minus. So you're going to get your H plus coming from your water, and then what you'll be left with is Al, H2O5, because now you only have 5 intact water molecules left, and the OH minus. Now the OH minus and the Al plus 3 reduce the charge to plus 2. The easiest way to get the charge is to just recognize that these must equal 3, because that's what the charge is on this side. Okay? So one of the waters splits, the hydrogen ion kind of floats away, this H plus leaves, right? And so what you're left with is this structure, okay? With 5 waters attached, Al has a plus 3, and the OH has a minus 1 for an overall charge of plus 2. So I'd like you to do C and D, please, on this part. And that's it for our first video. There'll be one more video for the weekend, and then you'll need to do the first homework. So I'll be back with the second video momentarily. See you guys.